When confronted with a random unsorted array of data, there are very few assumptions we can make regarding the rank of each individual value. Consequently, search patterns usually descend into a linear process where each value is sequentially evaluated until either the target is found or the dataset is exhausted. This yields a best and worst case complexity of O1 and On respectively, where n represents the number of values within the dataset. Conversely, however, by sorting the data prior to searching, we're able to make more informed decisions regarding the rank of a specific value relative to that of another. Examining the centermost element, we see that 96 is less than our target value of 256. As the sorted values situated to the left of 96 must also be less than 256, we can exclude them from all subsequent iterations. Continuing the process at the centermost element of the remaining dataset, we see that 192 is also less than our target value of 256. Once again, we exclude the values that cannot possibly be a positive match. Repeating the process to its logical conclusion, the target value is ultimately located upon its fifth iteration. Repeating the entire process with a search value of 80 instead of 256, we once again converge upon a target after its fifth iteration. As the binary search effectively halves the viable dataset upon each iteration, it yields a best and worst case complexity of O1 and O log n respectively. Let's take a look at a C implementation of this algorithm. We first define a function that accepts the target value, array pointer, and array length as its parameters, and subsequently returns a true or false value to signal the result of the search. Consistent with standard C practice, variables that represent the top, bottom, and comparison indices are declared at the beginning of the function. Prior to initiating the search, the bottom and top indices are initialized to the first and last elements of the sorted array respectively. A loop is constructed in such a way that it terminates only once the top and bottom indices have crossed over one another. At this point, we can assume that the target value was absent from the supplied dataset. The current comparison index is calculated as the midpoint element situated between the top and bottom indices. It's important to note here that both floor and ceiling midpoints are acceptable within this particular context. When calculating a floored midpoint, we first determine the difference between top and bottom indices and subsequently divide by 2. Applying the floor function, this value is further rounded down to its nearest integer representation. Finally, by offsetting the value relative to the bottom index, we determine the current floored midpoint as 5 plus 2. When n and d are whole and natural numbers respectively, it should be noted that n divided by d becomes an implicitly floored operation. With this in mind, we can simply restate the integer midpoint formula without invoking an explicit floor operation. Expanding and factoring appropriately, this can be further simplified as top plus bottom divided by 2. Given what we already know about floored division, calculating its ceiling equivalent is a trivial matter of incrementing the quotient when n is not a precise multiple of d. Therefore, the ceiling midpoint may be subsequently expressed as top plus bottom plus 1, divided by 2. Due to its marginally smaller profile, we've elected to use a floored midpoint for this particular example. If the array value referenced by the comparison index is equal to that of the target value, then a match has been made, and the function returns true. If the array value at the current comparison index is less than that of the target value, then discard all array values situated between the bottom and comparison indices, inclusively. Similarly, if the array value at the current comparison index is greater than that of the target value, then discard all array values situated between the comparison and top indices, inclusively. If the loop terminates, then no match was found and the function returns false. Performing a dry run of the code presented thus far, it should be noted that the answer is indeterminate when the sorted array is known to contain duplicate values of the same magnitude. Therefore, if it's necessary to distinguish between adjacent duplicates, then a bilateral scan needs to be performed upon completion of the binary search. Examining the code a little more closely, it's interesting to observe the final condition when the target value is not present within the sorted array. When the final comparison occurs at the bottom index and the array value is greater than that of the target, the top index crosses under the bottom and the search terminates unsuccessfully. As the magnitude of the target value is situated somewhere between the two values referenced by the top and bottom indices, they each represent the nearest low and high values respectively. conversely, when the final comparison occurs at the top index, whilst the array value is less than that of the target, the bottom index crosses over the top, and the search once again terminates unsuccessfully. Again, as the magnitude of the target value is situated somewhere between the two values referenced by the top and bottom indices, they each represent the nearest low and high values respectively. Therefore, whichever way the search fails, both top and bottom indices are always in a predictable state, providing they don't exceed the bounds of the array. When the top index underruns the bottom end of the array, it should be noted that the bottom index effectively represents both nearest low and nearest high values concurrently. Analogously, when the bottom index overruns the top end of the array, the top index also represents both nearest low and nearest high values simultaneously. With this in mind, it's relatively simple to refactor our first code example so that it returns the nearest value when the target value is not present within the sorted array. First, we redefine the function with an additional Boolean parameter, which determines if the nearest lowest or nearest highest value is returned upon failure. As this example is designed to return an array value whatever the outcome, it assumes an array length greater than or equal to 1. Consequently, the while loop is inverted for efficiency. If the target value is not found, they return the nearest low or high value in accordance with parameter 4. Whilst this is a common method of implementing the binary search algorithm, it's possible to adopt a reductive approach where the log n reduction is allowed to follow its natural progression. Again, we define a function with the same 4 parameters as previously implemented. As before, we declare and initialize both top and bottom indices, and also decrement the array length parameter for subsequent convenience. As the equality comparison is now deferred until the viable dataset has been reduced to a single value, the loop terminates just before the top and bottom indices cross over one another. As in previous examples, the current comparison index is calculated as the flawed midpoint between the top and bottom indices. If the array value at the current comparison index is less than that of the target value, then discard all array values situated between the bottom and comparison indices, inclusively. Conversely, if the array value at the current comparison index is greater than or equal to that of the target value, then discard all array values situated between the comparison and top indices, excluding the value referenced by the comparison index itself. As we no longer explicitly check for equality, it's important to note that the else condition now represents a greater or equal proposition. As this may include the target value itself, we must always preserve the comparison value when discarding the upper half of the current dataset. If the array value concurrently referenced by both top and bottom indices is not equal to the target value, then return the nearest high or low value, in accordance with parameter 4. Otherwise, both top and bottom indices concurrently reference the target value, so return the value referenced by either index. Running an example with this revised implementation, we once again begin the search at the flawed midpoint of the current dataset. As 96 is less than the target value, the bottom index is moved to the comparison index +1. Continuing at the new midpoint, as 192 is not less than the target value, the top index is moved to the current location of the comparison index. Again, as 160 is less than the target value, the bottom index is moved to the comparison index +1. Finally, as 180 is less than the target value, the bottom index is moved to the comparison index +1, and the search terminates with a positive match. Examining the revised code a little more closely, it's important to observe a final condition when the target value is not present within the sorted array. When the search terminates unsuccessfully, both top and bottom indices simultaneously reference the nearest high or low value depending upon its rank. Similarly, depending upon rank, the opposing nearest value is always situated one position below or above its terminating index respectively. As with previous examples, we also need to be mindful of the occasions when the terminating indices reside at the extremities of the dataset. When considering this reductive approach, there are 2 specific nuances we need to be aware of. Firstly, as the equality condition is implicitly encapsulated within the else condition, the search always converges at the bottom-most value of duplicate spans. Secondly, and for much the same reason, the comparison index must always be calculated as the flawed midpoint in order to mitigate the possibility of an infinite condition. Finally, if we'd rather have the search converge at the topmost value of duplicate spans, we need only invert the reduction condition and change the flawed midpoint to its ceiling equivalent.